The first and the foremost point is that when your physical condition remains same, right, which we have discussed in the previous class, when your physical condition remains same, then only we can apply Ohm's law, right? Hello everyone, my name is Vivin Abram, and in today's video, we will talk about Ohm's law in vector form. So in the previous video, we talked about Ohm's law. So this video will be just the addition to the previous part, right? Okay, so let's get started. Okay, so the first thing is that we will recap what we learned in our previous video, right? So what was your Ohm's law? For example, just look at this figure. We have a battery source. We have a resistance over here. It can be a conductor. It can be a normal bulb. It can be any electrical device that we use in our home, right? Okay, so we have ammeter over here. The work of the ammeter was to measure the value of current, right, that is flowing from your circuit. So obviously the circuit is complete, so we can simply say some I current will flow, right, and this ammeter is going to measure this I current, right? Okay, and then the current will continue over here, right, and some of the current will go to the voltmeter also, so that it can actually work, right? And then yes, the circuit will be complete over here, right? Okay, now what is the work of this voltmeter? Voltmeter will actually measure the potential difference across the resistor, and that will be maintained by the battery. Is that a yes or no? So according to Ohm's law, right, the current that is flowing through this resistor or the bulb or whichever conductor that you have placed over here, or the electrical device that you have placed over here, right? So the current that is flowing through that electrical device or the resistor or the conductor is directly proportional to the potential difference across it, right? It is directly proportional to the potential difference that is, across it, which is like maintained by the battery. It's pretty simple. So if the potential is more, the current will be more, and vice versa. If current is more, that means potential is more, right? So mathematically, we can simply write Ohm's law as V is equals to IR. Now this is something which we have learned in the previous video. So for all those who haven't watched, you can go and you can watch that video, right? So V upon I, the ratio of voltage upon potential difference upon the current, is actually a constant, and that constant is what we call as the resistance offered by the material, by the conductor, by the resistor, right, in the flow of current. You can actually imagine it as the hindrance provided in the flow of current, right? Okay, so this is your resistance, right? Okay, now you have to understand one very important point which you have to understand is the value of resistance does not depend upon the potential or the current. Now why I'm saying that? Because like I said, the ratio of V upon I is actually a constant. Now when I say constant, what does that mean? That means no matter how large my potential is, right, the current will also become large and it will nullify the effect, right? So for example, it is just like this. So for example, you have 1 upon 2, right? This is one ratio, 1 upon 2, right? And this ratio is also equal to, let's say you increase the value of, let's say you make it 2 upon 4, right? So you have increased 1 to 2 and you have increased 2 to 4, right? But at the end of the day, when you divide it, 2 1 is 2, 2 2 is 4, the answer still comes out to be 1.5, right? So very similarly, these V upon I, right, the potential and the current, that is like current that is flowing in through your circuit, and the potential that is across the resistor, it will balance themselves in such a way, right, that your resistance will always be constant, right? So you can simply say your resistance does not depend upon the potential or the current. Let's say you have increased the potential difference between the battery, right? Then what is going to happen? More and more current will flow, right? And then again the ratio of V upon I will be a constant. Is that a yes or no? So what is your Ohm's law? The current that is flowing through your resistor or the conductor or the electrical device that you are using is directly proportional to the potential difference across that material. Is that a yes or no? Right? Okay, let's move forward. Unit of resistance. Yes. Now this is named after the scientist who actually discovered Ohm's law, right? So the unit of resistance is ohm, right? It is given by this Greek symbol omega, right? This is a Greek symbol which is omega, right? You just simply write it like this. Let me just write it down. This is the sign of omega, right? It's a Greek symbol, right? So we call it omega, or in short form, we just say ohm, right? So you can simply say resistance can be of 1 ohm, 2 ohm, or maybe 1000 ohm, right? Depending upon our requirement, right? So resistance are the devices which are used to control the current, right? So you can put a resistor in between the flowing of current, and with the help of resistance it becomes very difficult for the current to flow through them, right? Depending upon the value, right? For example, if you have a resistance of 1 ohm, it will be very easy for the current to go. If instead of 1 ohm it is like 10,000 ohm, then it will be very difficult for the current to pass through that, right? So your resistors can be used to, to damp the motion of current, or you can simply say to reduce the value of current, or to reduce the flow of current in a circuit, or to control the current, right? So that is some of the uses of your resistance, right? Okay, so I hope you understood what is Ohm's law now, right? In the previous video we explained, also in this video also, I hope you understood that, right? Okay, let's move forward. Now we know very well that our Ohm's law is given as V is equals to IR, right? V is equals to IR, and I can compare this with our straight line equation for a graph, right? So mathematically I can write straight line equation of a graph. Y is equals to mx plus c, right? Where y is the y-axis, m is the slope of the graph, x is the x-axis, and c is the intercept of the graph. So for example, a graph is intercepting on y-axis or z-axis, depend, or your x-axis, depending upon the situation, right? So here when I compare this, right, v is equals to IR, so I can simply write it here, v equals to IR plus 0, in order to compare these two equations, right? So when I compare, I can see that my y-axis is actually voltage. Voltage is on my y-axis, right? Now m is something constant, which is known as the slope, right? So here you guys can see current is something which you can vary, so that means your x-axis is taking the value of current, and r is actually the slope here, right? And the intercept is 0. The value of intercept is 0. Now when the intercept is 0, that means your graph will pass through origin, right? That is the beauty of it. So if your intercept is 0, then that means your graph will pass through your origin. So basically you can see here on my y-axis I have potential, or the potential difference, right? On my x-axis I have current, my slope is resistance, and the value of intercept is 0. So these are the findings from your V is equals to IR equation, right? So when you simply make the graph, you guys can see along my y-axis, according to this, along my y-axis I have potential, right? Very similarly, along my x-axis I have current. You guys can see current is there, and as the intercept is 0, that means your graph will pass through your origin, right? That is 0 comma 0. It will pass through the origin, right? And you guys can see we have a constant slope. The resistance is constant, right? So you will simply get a straight line, right? So when you get a V versus I graph, and you get a straight line on a V versus I graph, that means the device is actually following Ohm's law, right? So that means the slope of the graph, right? The slope, let me say this is some theta, so I can write tan theta is actually the slope, which is equals to y2 minus y1 upon x2 minus x1. This actually gives me the value of resistance, right? I hope that is understandable to you, right? So whenever we talk about the slope of V versus I graph, we always get resistance as our answer. Is that a yes or no? All right. Now, the main topic was to represent your Ohm's law in vector form, right? Now you have to you have to look at this equation, V is equals to IR. Now here V is the potential difference, which is like a scalar quantity, right? I is the current, although it has direction, although it has magnitude, but again we all know that your I is a scalar quantity, right? Okay, now resistance is actually a constant quantity. It definitely don't have the direction. So obviously this entire equation is actually a scalar quantity, right? So this entire equation is actually what? Scalar, right? Now the the topic for today was we want to convert this scalar equation into a vector one, right? Now, how we can do that? Now, in order to do that, we need to define some new terms, right? Now, first new term that we have to define is what we call as our current density. So this is an alternative for your current. Now, let's try to understand how we define it. It is actually written as J. J is the symbol with a vector sign over it, right? Now let me try to explain what is your current density, right? Okay, so let's say you have a conductor over here. You guys can see a conductor over here, and let's assume that the current is some I current is flowing through this conductor, right? Some I current is flowing through this conductor. Now current density is defined as, you guys can see it's written over here, current density at any point is defined as the amount of current flowing per unit area around that point, provided the area is normal to the direction of current. Now you have to understand it is defined as, for example, at this particular point, let's say at this particular point you want to find out the current density, then you have to take a circular area over here. So I have taken a circular area. Now this area will be having some charge, and with that charge it must have been moving in the forward direction, right? So current density, that is your J, which is actually defined as the current per unit area, the current that is going per unit area. So this is let's say let me imagine a unit area over here. Now this unit area will be having some current and it is moving in the forward direction, right? So J is defined as, current that is moving per unit area, right? Now in the last part of the definition is written, provided the area is normal to the direction of the current. We're not talking about area vector, we're talking about area, right? So what is area? So area is this one. Area is perpendicular to the flow of current. The angle is 90 degree, right? Yes, so that condition is satisfied. So you have to understand area around that point. So the area around that point is moving in that direction, right? So this area will be having some charge and that charge is moving with that. So you will simply define it. J is equals to, that is the current density is defined as current per unit area. So you have to understand your current is not a vector quantity. On the other hand, your area vector is a vector quantity, right? So area vector is always perpendicular to the surface, right? So obviously this is perpendicular surface. So this is your area vector, and which is in the direction of your current. Is that a yes or no? Right? I hope that is understandable, right? Okay, great. So your current density, instead of current, I can talk about current density, right? Now density always talks about mass per unit volume. So for example, if I talk about mass density, that is mass per unit volume. Very similarly, current density, that means how much current is coming throughout any particular cross section area, right? That is what we call as our current density, that is your J, right? So you have to understand I is not a vector quantity, but area is a vector quantity. So your current density, that is J, will also have the same direction that of your area, and in a way we can say it will have the same direction as that of your current, right? So you can write it here, direction of J is along the direction of your current, right? So you have to understand we got one term, that is your current density, which can replace the value of current over here, right? I hope you guys can understand that, right? Okay, now if I have a conductor, right? So this is a conductor which is like connected with a battery source over here, right? And let's say this conductor is of some L length, right? Then I can simply say potential will be written as, yes, can I write it E times of L, right? And from here you can say your E is actually the vector quantity. The E is actually electric field, or I can simply say E is actually equals to V upon L, right? And where E is your electric field, which is a vector quantity, right? Now you got two things over here. You have J, which is like current density. You have electric field, which is defined as V upon L. And one more thing, from our previous video, we know the resistance can be written as R equals to rho L by A, where rho is your resistivity, L is the length of your material or the conductor, A is the area of cross section of the conductor, right? Now let's try to find out the vector form of Ohm's law. Now the famous Ohm's law is written as V is equals to I times of R, right? Now what I will do here, I will try to convert this V's and I's and R's in the form of the formulas above, right? So from here I can write my I is actually equal to J vector multiplied by area vector. Is that a yes or no? Right? Okay. From here I can write my V is actually equals to E multiplied by L. E multiplied by the length, right? And resistance is anyway written here. So I'll just replace this value. So instead of V, I will write this value, E times of L, right? So let me just write it here. E times of L, where E is your vector quantity, is actually equals to, instead of current, I will write J times of A. I will write J, that is your current density times of your area vector, right? Multiplied by, yes, I will talk about resistance. Resistance can be written as rho L upon A. Is that a yes or no? Right? Okay. So from here, you guys can see, if I talk about only the magnitude over here, E multiplied by L is equals to J multiplied by A multiplied by rho L upon A. So your area will be cancelled out from here, your length will be cancelled out from here, and you will left with E vector is actually equals to J vector times of rho. This is what you call as Ohm's law in vector form. That is, your electric field is actually equals to current density times of your resistivity. Sometimes you can write it like this also, 1 upon rho times of electric field is actually equals to J. And let me tell you, 1 upon rho is what you call as your sigma, which is your conductivity. Conductivity, it's a new term, conductivity, right? So you can write it like conductivity. So you have to understand, I can write sigma times of E electric field is actually equals to the current density. This is also one of the form of Ohm's law. So these two are your Ohm's law in vector form. Vector form. Why? Because obviously electric field is a vector form. J, that is the current density, is anyway vector form, right? And rho is resistivity, which is like constant for a particular physical condition. Okay, now let's talk about the limitations of Ohm's law. Limitations of Ohm's law includes very big limitation, that is it is very difficult for us to maintain the physical properties of the material, right? For example, I can simply give you an example. For example, you have a wire and the wire is having some current I. Now let's say a huge amount of current flows through the wire. Then what is going to happen? Suddenly the wire gets heat up, right? Slowly the wire gets heat up, and as the wire gets heat up, the temperature is increasing. So as the temperature increases, what is going to happen? The resistivity of wire changes, and as the resistivity of wire changes, it does not follow Ohm's law, because we know V upon I is actually your resistance, and with temperature resistance also change as your rho changes, right? We'll discuss about the properties of rho in the coming video, right? But you have to understand, as the temperature changes, the rho changes and the resistance changes, and it will not follow Ohm's law, right? For example, let's say I make a graph here. Let's say here I have current, right? Here I have potential difference. So let's say the graph was following Ohm's law, right? It is very nicely following Ohm's law, but at higher temperature, it deviates from Ohm's law, right? It will not follow Ohm's law, right? So when it is not following Ohm's law, then the relation between V is equals to IR, right? This will not be valid, right? V is equals to IR. This relation will not be valid. So very good example to this is that, for example, if we are having a smartphone, right? Suddenly the smartphone heats up, right? Why? Because let's say we are using some very heavy, very heavy application. So because of that, the system, the battery heats up, right? Now, as it heats up, you have to understand, as it heats up, the temperature of the entire device changes, and as the temperature changes, Ohm's law is not being followed, right? That's why your system start doing some crazy things, right? Sometimes your touch is not working, sometimes. So in the case of laptop gets hang, right? Because it is not getting that optimum temperature at which it should work, right? So very simple example is that as more and more current flows through your wire or through your material, right? So if it is, if it is the temperature of the material is actually increasing because of more and more current that is being flowing through your wire, so what is going to happen? The resistivity will change and the resistance will change, and Ohm's law will not be followed, right? So this is one of the limitations of your Ohm's law, that at higher temperature Ohm's law is not valid. So I hope you understood the video. I hope you understood something. So if you have any doubt, you can comment it down in the comment section. And in the next video, we'll talk about resistivity. So stay tuned, and thank you and have a nice day.